Thanks, Catherine, for the introduction. So can all of you see the screen? Okay. So again, thanks for inviting me. And when Catherine sent me the abstract of the project, I found it very interesting. The main reason is I'm a methodologist. I'm interested in data. And just looking at the title, then it includes social ecological life course approach. And when I read the abstract in more details, also find it would be a longitudinal data. So in terms of data structure, it will be quite interesting as it involves family, individuals, probably environment, and also longitudinal. So it fits nicely into a multi-level model. So since I have no idea about the content, so that's why there are lots of experts here in this panel. And so I think maybe it's a good time for us to recap a little bit about nested data. And there are two main messages. The first one is what are the issues with them? Can we just ignore them and pretend there's no problem? So that's the first one. So it's a bit negative. On the other hand, we also see opportunities when we are dealing with nested data. In fact, we can ask more interesting research questions. So I hope in these few slides we can recap a little bit about our understanding. So first of all, probably all of us have taken some introductory level modules, regardless of whether you're students, researchers, or even professors. For us, it would be decades ago. And when we are using these techniques like t-test and ANOVA, multiple regression analysis, and even more complicated one like a structural regression model, we have some base assumptions. And independence assumption is one of them. So what's the meaning of independence of the data? Okay. So now let's imagine we are interested in some individuals, some family members. So we can look at it as they are family A, and then within each family A, then there are a couple of members. And then within family B, there are also another 2 members. And for family C, there's only 1 member. And when we look at the data structures, they are not independent. It means that for participants within the same families, they are more similar because they share similar environments, they share similar resources. So in terms of educational background, resources, then we expect family members within the same families will be more similar than each other when compared to participants in other families. And if we look at it from this perspective, then we can also increase the data nature or move it up a little bit. And in here, we just consider the families related to, so all of them are from the same countries. But we can also imagine the families, in fact, they are nested in regions, the neighborhood, and they are they're living in similar regions. Then they also share similar public facilities. And there are also some similarities when we compare participants or family from one region to another. So in fact, the reality is much more complicated than we think. So if we just use simply classification, we just consider as level 1 and level 2. So we can see students are nested within schools. So when we compare students across schools, of course, we are all under education. So we all know schools do have some effect and impact. Students within the same schools are more similar in terms of performance, or in some cases, emotions, personalities, and other resources. And people within countries, of course, when we're comparing participants across countries, we observe some effects. So also sometimes they are stereotypes, but sometimes there are real differences. And within departments, we can also see there are also some similarities and family members, of course. And then the final one I also want to highlight is even within the same person, the same individuals, if we are measuring the same individuals multiple times, then our data, in fact, can be considered as nested data. Now our data are level 1, and then the participants are level 2. So simply speaking, what we are meaning by nested data means the data structures, we can clearly classify them under a particular group, a particular family, countries. And we just try to make it easier for us to understand. In reality, the situation is much more complicated. For example, we may have repeated data and for under individuals. And then for the individuals, they're also nested within families, and families may also nested within regions. Then as researchers, we need to make a call to decide how to design the nested structures. In theory, we should add all of them, level 1, level 2, level 3, level 4, in order to address the question. But sometimes we may not have enough data. So we may just want to focus on, let's say, 2 levels or at most 3 levels occasionally. But it will be some issues and problems if we just pretend the data are independent. So that's the first message. Then what are the problems if we treat the data as independent, if in fact they are not? So let's look at an index. How can we tell whether the data are independent or not? We have an index we call intra-class correlation, ICC. So it's a very useful and simple index. So in general, it varies from 0 to 1. If the data are independent, they are not related, then they are zeros. For ICC equals 0, it means if we know one member of the data, then it doesn't help us to predict the characteristic of another member. In other words, if we have 100 participants in your data, knowing one of them doesn't help us to guess what's the feature or what are the potential score of another. However, if the data is not independent, for example, ICC equals 0.3, then it means 30% of the variance of data can be explained by the grouping factor. So let's use the same examples. Suppose if we know the data of one member, and then if we need to make a guess, what would be the other member's characteristics based on the data we have, this particular member, then we can make a pretty good guess in some sense because they are not totally independent. So it's quite helpful. And if we treat them as individuals, then we'll make some critical errors. Okay, so what will be the errors? When we are doing research, then many researchers use hypothesis significant testing. Whether you like it or not, in some sense, we still need to report the p-values. And conventionally, if the p-values are smaller than 0.05, then we claim it statistically significant. And how does the ICC or the non-independence affect it? So let's consider the most extreme case first, the ICC equals 0.2. Okay, so in this case, so it means it helps us to explain about 20%. On the other hand, the x-axis represents the number of groups. Sorry, the number of members in the groups. We start with 10 members, 25, 30, and 100. And then the y-axis indicates the true or the observed rejection rate. So in theory, the correct rate would be 0.05. Okay. So where is the line? So let's look at the black line, the ICC equals 0. So we can see a black line here. In other words, if the ICC is 0, then it doesn't matter what's the size, the group size. We can always guarantee that the p-value is accurate. So if we say that it is 0.05, then it is actually 0.05. That's a good thing because we won't over-reject the null hypothesis. Let's look at the worst case scenarios, the red line. ICC equals 0.2. If we have 10 members from the same groups, for example, from the same classrooms. We have data from different classes, and then we put them together and ignore that they're from the same class. When we claim that the p-value is 0.05, the actual p-value is here, 0.3. Okay. So in other words, even though there's no effect, there's 30% chance that we'll incorrectly reject it. Well, from the researchers' perspectives, they could be quite happy because they find significant results, but unfortunately, these are misleading. These are incorrect results. And this rate also increases according to the number of groups. For example, if we have 100 members per group, then actual rejection rate can go up to 0.7. Okay. So this is quite common if we are doing cross-cultural research. If we have members from different countries, from some large international cross-cultural project, if we ignore the countries and conduct something we sometimes in the past, in the old days, we call pan-cultural analysis, and ignore the data independent, then you can imagine the inflated type error could be 0.8 or even 0.9 because the number of members per country can go beyond 100. So again, you find lots of significant results, but in fact, they are misleading. Okay. So from here, we know that we can't simply ignore the independence of data because it will lead to inflated tyrant errors. And unfortunately, some researchers are not aware of it and then just pull the data together. So how can we address these issues? So in the literature, across different disciplines, not only in psychology, sociology, economics, and also in sciences like biology, or about statistics, they develop ideas to handle this class of models. And interestingly, even though the disciplines are very diverging, but the mathematical models are always identical, so we can call them either multi-level models in social sciences or mixed effects models in physical sciences or biostatistics. And there are also other names. For example, in education research, we call hierarchical linear model, variance components model, random coefficients model. So the key idea is we consider the data as nested. They are level 1, level 2, or they can also be level 3. Let's illustrate the simple ideas using an education examples. So this is a famous data set in multi-level models. When we are introducing it, we sometimes use this as an example. So it's from a national representative sample of the US public versus Catholic high schools. And it consists of more than 7,000 students nested within 160 schools. The level 1 variables means the students' data. The mathematical achievement is the dependent variable. And then the independent variable is SES, socioeconomic status. So the key research questions, what's the relationship between SES and mathematical achievement? Based on common sense, and also lots of research, we know that SES is an important predictor of mathematical achievements due to various reasons. For example, resources. If students have higher SES, their families tend to have more resources, and also the parents also tend to have higher educational levels. Then for the level 2 variables, in here we have a sector. So in the US system, they are public versus Catholic schools. So we can also ask, would the same effect varies according to whether they are public school and private Catholic school? And one interesting research question here is we have 2 types of variables. One is at level 1, and then the other one is at level 2. Then we may use level 2 variables as both predictors and also moderators. And if we are doing, let's say, data analysis, then we can also ask interesting questions like whether the families as a level 2 variables or the neighborhoods can be used as moderators or predictors. So since I'm not going to present any math, so let's look at figures. So in here, I just selected 20 schools for illustration. The x-axis is the SES, and then the y-axis is the mathematical achievement. So if we just take a particular school as an illustration, if we plot them, then it seems that we can see a slight trend here. It seems SES is positively related to mathematical achievement, but this effect varies. On some schools, the effect is stronger than others. So it's not easy to look at a pattern. So let's try to get all the intercepts and also the slopes together and combine them in a single graph. So we can see we can easily get some sense how it looks like. So in these figures, the x-axis is the SES, then the y-axis is still mathematical achievement. And each red line represents one school. Okay, so for example, this line, the slope is quite strong. It means that in this particular school, the effect between SES is very strong. On the other hand, for some schools, they look like flat lines. It means in these schools, the relationship between SES and mathematical achievement is much weaker. Okay. So this makes sense. We don't expect the same relationship holds in all schools. So some are stronger, some are weaker. Then if we have lots of slopes, we can get the average. So the black line represents the average intercept and average slope. So from here, we can get our first conclusion. In this case, let's call it observation. Okay. On average, SES and mathematical achievement is positively related to each other. But we can also see this relationship varies across schools. Some are stronger than others. And this is the key idea or perspective of a multi-level models. When we are conducting a multi-level model, we are not only interested in the average, like the black line. We are also interested in the variation, how different schools vary across this average. And then we will also want to ask why some schools have larger slopes than others. Okay. And luckily, a multi-level model framework allows us to address all of this question. Okay. And if you still recall, in our data, we are also interested in public schools versus Catholic schools. Okay. So in the further analysis, so I skip all the math and also analysis and just present the results graphically, so we can get some ideas what kind of research question can be answered by using a multi-level model. In this case, we have a public school, which is the blue line, and also the Catholic school, the red line. Okay, and the difference between them is statistically significant. In other words, the effect of SES on the mathematical achievement is stronger in public schools. Okay, so by the way, it doesn't mean that it is not important in Catholic schools, but it clearly tells us that it is more important in public schools. If you have good SES, then the effect on the mathematical achievement is more important in public schools. For Catholic schools, there are other factors that contribute. Okay, so in the previous example, we look at cross-sectional data, and I've also mentioned for longitudinal data, we can also use the same perspectives, and that's a very nice thing. We can combine, integrate cross-sectional with longitudinal data in a more unified framework. So in here, for each individual, so a participant A, then we measure them 4 times, time 1, time 2, time 3, and time 4. And then for another participants, we only managed to measure 3 time points, and there's a missing in the last time point. We couldn't measure it. Okay. And in multi-level models, we can handle missing data quite easily. It means we don't need to do any imputations or also deletion. The whole framework can handle incomplete data automatically. So it's much better than the traditional repeated measures because it assumes all the data complete. And we use an artificial example to illustrate the idea of analyzing longitudinal data. And probably you notice in a minute or soon later that the research analysis or the question are almost identical to those we have mentioned in the cross-sectional data. Because in theory, they are almost the same with some minor exceptions. So in this case, we have children and then we measure their antisocial behaviors. So these are the level 1 variables. So the dependent variable is antisocial behaviors of the children over 4 time points. And we use the time 0, 1, 2, 3 to represent them. And for the level 2 variables, they are gender, male versus female. Okay. So this is a kind of interesting. When we are analyzing cross-sectional data, the individual features like gender is level 1 variables. But when we are analyzing longitudinal data, because the level 1 data will be the time, the antisocial behavior measured at 4 time points. So the individual level variables become the level 2 variables. Okay, so we use this as a moderator. And you can also see a clear similarity between this variable and the previous one, public versus Catholic schools. So our research question is still the same. But now our predictor, the predictor is time. So we are interested in how the antisocial behaviors vary over time. We use the same approach. First of all, we can look at the children's one by one. So let's just pick this particular child. So we measure them 4 time points, and then we can see there's a linear positive trend. So in other words, this child becomes more and more antisocial over time. Okay. But for others, they're more stable or more similar. And for another one, it goes down a little bit. Okay. And by the way, just as a side note, how can we handle incomplete data? So in this case, there are 4 time points, but if they're missing data, it simply means that we may have, let's say, 3 time points for particular individuals. So it handles it in a way that we don't need to delete or impute any data. Okay. Then we are using the same approach. We can extract the individual slopes and intercepts. In here, each red line represents the line for one child. And we can notice, for example, this particular child, he or she becomes more and more antisocial over time. In fact, it changes from 1.2 something to 6 in this scale. But for others, in general, they're quite stable. A couple of them goes down. Okay. And if we take the average on the intercept and the slope, we can draw a blue line represent an average slope for all children. In here, just 20 participants. Okay. And in this case, we can also see there's a very small increase over time. It's not a lot, but it seems that there's a positive trend. Children becomes a little bit more and more antisocial over time. Okay. But there are variations, lots of individual differences. Some are more antisocial than others. Okay. Then we can also compare males and females. Okay. Then we can look at the effects for males, the blue lines, and also the effects for females, the red lines. Okay. And in here, we can find 2 observations. The first one is when we look at the start or the beginning of the project. So this is a time 0. So this is the first measure, the first occasion when we are measuring the children's. There's a clear discrepancy. Boys are more antisocial than girls. So this fits into our stereotype, and probably I think lots of literature when we are looking at it. But how about the change over time? If you're looking at the trend in this case, in fact, in the actual data illustration, is not significant. then we can see it. The slopes for both the males and females, they are identical or almost identical. In other words, in general, over this measurement, the period, boys are always more antisocial than girls in terms of measurements, and there's no change in terms of the slopes. Okay, so to conclude, I hope these few slides and these very brief presentations can give you a non-technical introduction to what nested data are and how to analyze them with multi-level models. So again, let me repeat the messages. First of all, if the first one is we cannot ignore and pretend the data are independent. Otherwise, our observed p-value would be much smaller than actual p-values, and we will make lots of false significance. Secondly, multi-level models are mixed effects models, a well-established methodology to handle this kind of data. Apart from adjusting and correcting the tyrant error, they also allow us to address and answer the research question from more integrative perspectives, because we can have individual level data and also level 2 or other higher level data structures. And we can address new research questions from different perspectives. And secondly, we can also extend this framework to sometimes we call cross-classified data. It means that they are also non-independent, but they are not fully nested. One simple example is the data in primary school and secondary schools. Okay, so children's moving from primary school to secondary school, they are not, for example, if they are from the same primary school, then not all of them would go to the same secondary school. So they are not nested. They will go to other, or some of them may be overlapped, some of them may be to other secondary schools. And also, when we are look at data between secondary school and also tertiary at our universities, they are also not fully nested. And now, under the same framework, we can handle and address all of these questions. Okay, so I'll stop here. Thanks for your attention, and welcome for your comments and suggestions. Thank you.